Hey guys, these are your notes on standing waves. Alright, so standing wave, definition first. It's a wave confined to a certain medium. Basically, a standing wave doesn't move from one location to another, but it stays confined in one space. Alright, the way we draw a standing wave is right down here. Here's an example of the second harmonic drawing of a standing wave, so it basically means two humps. And each hump is called an antinode. We label it with an A. Alright. In between each antinode on a standing wave is a node. So you see in the middle there, between the two antinodes is a node. And at each end, because they're fixed, is a node as well. You may have seen, standing waves have antinodes and nodes, and you may have experienced a standing wave before in a larger like confined medium. When you stand in the mall on the second floor, if you just kind of like stand still, you'll experience that at certain points the second floor does move up and down a little bit, just to kind of give, because there's so many people stamping on it all the time. It tends to move and it has a wave inside of it, and you could feel that. So next time you're at Garden State Plaza, take a second out and just stop and feel that there is a standing wave, not just in a string like an instrument, but any medium can have it, such as the floor of a mall or a bridge. If you've ever seen the Tacoma Narrows Bridge that collapsed due to a wave inside of it. Alright, so what is the node and antinode in a standing wave? A node is a location with no amplitude. It doesn't move up and down. And an antinode is the opposite of a node. It does move up and down, and it's the location with maximum amplitude to its movement. The way we draw a standing wave is I draw a solid line wave, and I just draw dotted lines mirroring that, either on the bottom or top, to show that that medium does move from the dotted line to the solid line and back over and over again. All right. So. Alright, standing waves have different harmonics. This is the second harmonic because there's two antinodes, two humps, basically. The third harmonic would have three antinodes. So the number of antinodes tells you the harmonic number in a standing wave. You just count the antinodes, and that's what harmonic you're in. Alright, so you could see from like this picture that there's always one more node than antinode as well. Let's talk about how to measure wavelength of a standing wave. The definition of wavelength is a crest and a trough together. How long is one crest and one trough together? So basically, to translate that definition into for a standing wave, it's the length of not just one antinode but two antinodes, crest antinode and trough antinode, kind of together. All right. So the length of two antinodes is the wavelength. So let's kind of just look at these pictures of the different harmonics and see how if we could measure the wavelength. It's the length of two antinodes. Well, actually, let's start with the second harmonic. I think it's easier. You can see the second harmonic has two antinodes. So simply, the length of your string is equal to the wavelength in that case. All right, so in this case, the wavelength equals 4 meters, because the second harmonic consists of two antinodes, so the length and the wavelength are equal. Now let's kind of kick back to the first harmonic. How do we find the wavelength in the first harmonic if it only has one antinode, but we want to know how long two antinodes are? Well, what we could do is we could double the length of your string. Two of these gets you two antinodes, and that equals our wavelength. So 2 times what's the length? 4. The wavelength would be 8 meters, because it would be like 2 antinodes, all right? Because we only have one. 1 is 4 meters, so 2 would be 8 meters. In the third harmonic, the wavelength again, it's the length of 2 antinodes. So it's 2 out of the 3 antinodes that exist. 1, 2, 3. So 2 out of 3 means 2/3 of the string which is L. So 2/3 of 4 gets you the wavelength. See, 2 out of the 3. So what is 2/3 of 4? It's 8/3, or if you do that on your calculator, 2.67. If we round to 2 decimal places, 2.67 meters would be the wavelength, the length of 2 antinodes. As you can see, we go from first, the wavelength's really long because the waves are stretched, smaller waves in the second, even smaller wavelength in the third harmonic, and the fourth harmonic, again, what's the length of 2 antinodes? That's the wavelength. Alright, so we're going to ask that. It's 2 out of the 4 antinodes this time. Gets you the wavelength. 2 out of 4 times the length of the string gets you the wavelength. 2 out of 4, what is that really? That's a half. Half of 4, again, is a shorter wavelength than the third harmonic, 2 meters for the wavelength. So the wavelength comes all from the picture. If you could kind of just look at it and see how long 2 antinodes are, that's the wavelength. Okay. Each there's an equation for standing waves we're going to use right up here, and it just tells us basically we could calculate, what pitch is made by all these different harmonics on a string. So it calculates F, frequency. Now, the equation goes as frequency of N. So frequency of the nth harmonic equals NV on top divided by 2 times L on the bottom. N is the harmonic number. So you could do F1, F2, F3, F4. That's the frequency from all the different harmonics. Right? And as we know, all those different harmonics on a string occur at once. The first, the second, the third, and the fourth, and so on, occur all at the same time and play this nice song together when you pluck a string. Now, N is the harmonic number, V, velocity of the wave, L is the length of the string, and F is the frequency. All right. So, let's start out with a picture of each harmonic and just kind of fill in this table. So the first harmonic means 1 antinode. There you go. Second harmonic means 2 antinodes. I'm just going to label the antinodes so you know. Count the antinodes, and that gets you the harmonic number. The third harmonic, 3 antinodes. And the fourth harmonic, down here, is 4 antinodes. A. Alright. So the wavelength, right? Here it would be twice the length of the string, right? And from before, this would just be L. Wavelength is 2 antinodes. So here, wavelength just kind of continues. Here the wavelength is 2/3 of that string, 2 antinodes. Here the wavelength is 2/4 of the string. 2/3 L, 2/4 L. And what can we write 2/4 as, really? 1/2. Alright. So what I'm going to do, just to finish this up, is we're going to calculate the pitch made by every string. Alright? We're going to say that the string has a length. A guitar string is about 0.8 meters or 80 centimeters. That's the length of a pretty normal guitar string. Alright? Now, which one are you going to use for L in this formula, though? 0.8 or 80? Always use meters. Alright, so we're going to use 0.8. So here we're going to write F1, the frequency of the first harmonic, NV over L. What is N? It's the harmonic number. V is velocity of a wave through a guitar string. We'll go with about, that's pretty fast, so we'll go with about 500 meters per second is our velocity. I'm just going to give that to you as a given. For that medium, it has a guitar string has about 500 meters per second of speed. Over 2 times 0.8 meters. So what's this come out to? 500 divided by 1.6 gets you, you know what would be nicer actually? Let's just choose, sorry about that, let's choose a 1 meter string. I think it's going to illustrate this a lot better actually. So 2 times, not 0.8, but let's go with 1 meter. Sorry about that. So 500 on top, 1 times 500 is just 500. 2 on the bottom, that gets you 250 hertz. So that's what you hear from the first harmonic on this string. Now on top of that, being played at the same time is the second harmonic. All these harmonics exist at the same time on the same string at once. So the only thing that changes is that we're calculating the second harmonic's frequency, so n equals 2. It's still a 1 meter string. It's still the same wave speed through that string. Alright? But now we just have the next harmonic, and when you multiply them out, you get 500 hertz. And again, the same thing for F3. N is going to be equal to 3 for the third harmonic frequency. Same wave speed, 500. 2 is in the equation, and again, we're going to just use 1 for the length of the string, 1 meter length string. So 3 times 500 divided by 2 gets you 750 hertz. You could do it yourself on your calculator. It's going to get you 750. Finally, F4 is n equals 4, 500, same wave speed, same length of the string on the bottom, and that gets you 1000 hertz. Now there's a pattern going on here when we use this equation. The first harmonic was 250 hertz, that was F1. F2 was equal to 500 hertz. The third harmonic and the fourth harmonic, the third was 750 and the fourth was 1000. How do you go from one harmonic to another? If you know the first harmonic, its frequency is 250, then how do you get the seconds? Well, you could add 250 to it. And how do you get the third? Add what again? Add 250 again. And how do you get the fourth? Add 250 again. So that's one way to look at it. But another way to do it is the first harmonic has a special name. It's called the, and write this down, it's called the fundamental frequency. So here, F1 is 250 hertz. Write down, that's called the fundamental frequency for this string. Every string is going to have a different one. But this string had a fundamental frequency of 250 hertz. It's the loudest frequency coming from that string. Alright, so when you pluck a string, 250 hertz is the primary tone you hear. But you hear all these other harmonics too. Alright? To get the second frequency, what you could do is you could take your fundamental, let's just kind of write that as F1 in general here. You could take your fundamental and do what to it? You can double your fundamental. That's your fundamental. You could double your fundamental to get your second harmonic. What could you do to your fundamental to get your third harmonic? You can triple your fundamental to get your third harmonic. So like 250 times 2 gets you the 500, and 250 times 3 gets you the 750. And again, you know, if you want to find the 10th harmonic, what do you do to your fundamental? Multiply it by 10. All right, if you want to find the millionth harmonic it exists, it's just really quiet. You take your fundamental and you multiply it by a million. All right, so just multiply your fundamental basically by whatever harmonic number you want to find, and that's how you get it. All right.